Okay, good morning, good afternoon, and good evening. Welcome to the MOF 2024 series webinar. So we are going to organize a series of webinars to prepare for the 9th International Conference on Metal Organic Frameworks and Open Framework Compounds to be held in Singapore on 15th, 19th July 2024. So before today's webinar, let me give you a brief introduction of MOF 2024. Here is a brief conference background and the significance of the conference. If your research is on crystalline porous materials like metal organic frameworks, covalent organic frameworks, and other porous materials, then you shouldn't miss this conference. It is the most well-established conference in the field with close to 2 decades of history. The first International MOF conference was held in 2008 in Germany. And after that, it has been held in France in 2010, UK 2012, Kobe in Japan 2014, Long Beach, USA 2016, Auckland, New Zealand 2018, and due to the COVID, the 2021 was held online. The most recent one, face-to-face, was held in Dresden, Germany, 2022. The next one, the MOF 2024, will be held in Singapore. We are very proud to host the MOF 2024. Singapore is a country at Southeast Asia. Here you can enjoy different food, different site views, and also a very rich metropolitan life. So we warmly welcome you to come to Singapore. Here are the conference themes and topics. So in the MOF 2024 conference, we are going to discuss mainly the materials, including not just the porous materials, but some other materials that can be of interest, such as 2D materials. We will discuss the fundamental phenomena and the properties, the synthetic methods, the characterizations, and applications and the industrial integration. This conference is supported by the Material Research Society of Singapore, together with the National University of Singapore, Nanyang Technological University, Singapore University of Technology and Design, and the Agency for Science, Technology, and Research, A*STAR. Here is a brief conference schedule and the dates. Before the main conference, we'll have a 2-day pre-conference to be held on 13th and 14th of July 2024. It will be held at the NUS campus. During the 2-day pre-conference, we have 1-day symposium for the young researchers. And the second day, we will organize a materials characterization workshop in which we are going to introduce many advanced material characterization methods, such as electron diffraction and X-ray absorption. And we believe those methods will be very helpful for those who are working in the MOF and the porous material area. So the main conference will start on July the 15th, and then will last until July the 19th. So we target about 1,000 participants. We have 2 special speakers who are the pioneers in the MOF field, Professor Susumi Kitagawa from Kyoto University and Professor Omayagi from UC Berkeley. And the conference so far, we have confirmed 8 plenary talks, 47 keynote presentations, 47 invited presentations. We would expect close to 200 oral presentations with more than 650 posters. In addition, we are going to organize editors forum and industry forum. So in those forums, you have the chance to interact with editors and also with industry partners in this area. We have gala dinner, and we also have some social visits for you to explore and enjoy your stay in Singapore. So these are the 3 important dates. The abstract submission deadline is January the 31st, 2024. And you will be notified of your abstract submission outcome in March 2024. The early bird registration deadline is 15 April 2024. So please make sure you register before that in order to enjoy a discount. So here is the official website of MOF 2024. We also have social media platforms in Twitter or X and WeChat. So please join us and follow the latest progress of MOF 2024. Before we start today's webinar, I want to introduce the next webinar. The next webinar will have a theme on MOFs in catalysis. It will be held on January the 16th, 2024, 8 p.m. Singapore time, 7 a.m. EST time, and 1 p.m. CET time. So please register. Beside me, we have 3 speakers in next webinar: Professor Micha Dinka, Professor Philip Miller, and Dr. Constance Newman. So we are going to discuss the most exciting directions in the MOFs in catalysis. Please stay tuned. All right, so that will end the introduction of the MOF 2024. So please allow me to introduce the speaker for today's webinar, Professor Jiami Qin. So let me give you an introduction of Professor Jiami Qin. Professor Qin, originally from Singapore, earned her PhD at MIT under Nobel laureate Professor Richard Schrock. She joined Emory, which is a research institute of A*STAR in Singapore, where she contributed to Emory's research on coordination polymers and started her independent career. In recognition of her work, she received the 2013 O'Leary Singapore for Women in Science National Fellowship. In 2014, Jiami joined the University of Zhao as a lecturer and later moved to the University of Vienna in 2019 as an assistant professor. In 2020, she secured an ERC Consolidator grant for research on field manipulation of MOF materials. Her current interests span bio-inspired materials, particularly methods to structure materials to improve their application performance. So in today's webinar, she is going to talk about controlling MOF materials across multiple length scales. Without further ado, let's welcome Jiami. Jiami, the floor is yours. Sorry, Jiami, you are muted.
Hi, sorry about that.
Yes.
Thank you so much, Ben, for the kind introduction and also the opportunity to join all of you here today to share some of the work from my group. So I'd like to talk to you, all of you, about our group's work on how to control MOFs across multiple length scales and the impetus for us to study. My screen is, there you go. So the impetus for us to study this is because when we look around us in nature, we see that there are many, many examples of biological composites, such as in the iridescent hummingbird's feathers, or in seashells, which are very, very tough, despite being made primarily of calcium carbonate or chalk, which we know to be notoriously brittle, or in the structure of a leaf. And all these biological composites have functionality significantly greater than the sum of their parts. And so for us, that's a very fascinating observation. And one of the keys to nature's ability to produce composites like this is its ability to structure these materials from the molecular to the nano to the micro and then the macro scale. And so the question is, how do we do that as scientists? So chemists, we typically are very comfortable with structuring things at the molecular level. You've got civil engineers at the other spectrum of the length scale dealing with infrastructure and on very, very large scales. But then it's the scales in between, from like the molecular, usually to the meso scale, that is really a challenge. So we are interested in MOFs because they are a class of molecular materials, which are typically formed from metal ions or metal clusters. And then you can choose different types of organic linkers to bridge them and then form these kind of frameworks, 1D, 2D, 3D frameworks. This modularity makes them very, very versatile and tunable, so you can use them for a lot of different applications. But we are interested in MOFs, not just because of this, but also because they serve as a beautiful platform for us to really manipulate them. So these molecular materials can be structured, as I already mentioned, at the molecular scale. But then one can move on towards the mesoscale using crystal growth and different techniques to control these crystals, and then look at their assembly into liquid crystals or using fields to manipulate them, and integrate these kinds of bottom-up assembly with top-down fabrication, such as 3D printing. So it serves as a very interesting platform for us to kind of play with. And so let's focus first on the molecular to the mesoscale. And quite a while ago, in 2009, the Kitagawa group showed that they took this copper naphthalene dicarboxylate Dapco-based MOF, and they reacted this material in the presence, or they grew this material in the presence of a modulator. So in the conventional method of growing metal organic frameworks, you usually have a metal ion, you usually have your metal source, your organic linker, and then you react it, and then you let these crystals nucleate, and then they slowly grow into bulk crystals. But you also can throw in a modulator, and when you do that, this modulator, which has the same functional group as the organic linker, but it only has one group instead of two, so it can't kind of extend these material into a framework, it will compete with this organic linker. And so you have these interactions that modulate how fast these crystals nucleate. And you also have selective interactions, which then lead to different types of crystals shapes as well. So when we first started working on MOFs around 2013, we thought, okay, so let's look at a very well-established MOF. In this case, we chose MIL53 with an amino functionality. And this MOF is characterized by an aminoterephthalic acid linker as well. And it's typically synthesized with an aluminum nitrate salt. And when you synthesize these in this manner, typically you get cuboidal shaped crystals. However, if you throw in acetic acid into the mix, what ends up happening is that this acetic acid starts to kind of compete with the carboxylate groups of the aminoterephthalic linker. And it selectively binds to these purple facets you see here. And so it inhibits the growth of these facets more so than the growth of the purple facets. And what happens is that you not only kind of slow down the growth of the MOF, but you also end up with crystals of different aspect ratios. So we found that actually, if let's say you take these materials and you throw in 30 equivalents of acetic acid, depending on which solvent you use, you get completely different types of morphology. So in water, you get like you do get rod-shaped crystals, but they don't have as high aspect ratio as if you had them in DMF. And the reason for this, we speculated, was because these linker here actually exists in part in the pseudo-ionic form in water. And so it has this carboxylate deprotonated, and that is able to compete more effectively with the acetic acid. So this modulating ability of the acetic acid is limited. So you can also play with the nucleation rate of these crystals. And so let's say if you were to throw into the mix sodium hydroxide instead of acetic acid. So in this case, this base deprotonates these linkers, and then you get a very rapid nucleation and you end up with nanocrystals. However, if instead you use a base, but with the acetate in the mix, then what happens is that you not only get really small nanocrystals, but they also happen to be rod-shaped. So we thought, okay, let's try using a different precursor instead of aluminum nitrate. Let's look at gamma alumina as a precursor instead, because gamma alumina is quite reactive, and maybe it could serve as a substrate for MOF growth. So we took AAO, these membranes for our gamma alumina source, and the AAO typically looks like this. So if you look at the SEM image, you've got this like slightly rough surface, and if you cleave it, you've got these kind of like nano channels that run through the membrane. So when we took the terephthalic acid, reacted it with our AAO membrane, what happened was that we get these like cuboidal shaped crystals, but in this case, they grow directly on the AAO, and you get, a full coverage of the substrate. However, if you throw in acetic acid, then you really massively slow down the growth, but you also get these kind of microflower type structures all over the place. And so you get basically these microneedles, but then they start to nucleate, and then they like form these flower structures. But then we looked around a little bit, and we found that like besides these little flowers, we see patches of these MOF needles that look like kind of blades of grass. And if you look carefully towards the edges of these patches, you get these needles that are kind of splayed out a little bit more. Whereas towards the center, where you get slightly denser growth, you actually see that the needles are actually a little bit better oriented relative to the ones here. So they are a little bit more vertical. And so when I first looked at this, I thought, what's going on here? And it turns out that this is a well-known phenomenon in crystal growth, which is called evolutionary selection, described by Van der Drift in 1967. So what is evolutionary selection? So simply put, let's say you have some crystals on a substrate and they're growing out. And so let's say the big red arrows are their fastest growing direction. So if these crystals happen to be growing with their fastest growing direction vertical, whereas you have some crystals that are neighboring it where they happen to nucleate and their fastest growing direction is not vertical, or let's say it's even worse, it's horizontal, then very rapidly these crystals start to see their growth inhibited because they grow into their neighbors and then their growth is blocked. So what ends up happening is that you start to select for these crystals that happen to be growing vertically in the fastest crystallographic direction of growth. And so in this case, you have a very dense growth that kind of selects for this vertical growth of these nano or micro needles. So we thought, okay, maybe we could try to kind of densify the structure, and maybe we could think about using the nano seed crystals that I showed you earlier, and effectively kind of seed the lawn, if I want to push this analogy further. And so if we seed this lawn of AAO, maybe we could increase the density of this moth grass that is growing and get them all vertically oriented. So what we did was we took some AAO membrane, we seeded it with these nanoseed crystals, and then we grew them where the AAO was supported on a glass slip. So this AAO happens to be porous, right? So like ligand can kind of go through and start to react. And so this actually reacts both on the bottom side as well as on the top side. And so the growth starts to etch the membrane, and it kind of starts to grow these monolayer of these microneedles. And what you see is something like this. So on the top, you have microflowers that are growing on top of a monolayer of these microneedles. But then at the bottom, because you have this glass slip, it blocks the microflower growth. And you end up with this monolayer of very nicely aligned micrograss. And when we looked at it, we thought, okay, this is actually kind of reminiscent of a Cassie-Baxter model for a superhydrophobic surface. So that is classically used to describe surfaces like the lotus leaf, which is a well-known superhydrophobic material. And so we thought, okay, maybe we could make these materials superhydrophobic. In this case, we would have to functionalize these amino MIL53 because it starts off as very hydrophilic. And so we thought, well, amino MIL53 has this handy little amino group here, which we could then kind of react with different reagents and install fluorocarbon groups onto it. So we did that using acyl chlorides with fluorocarbon chains. And what we ended up seeing was that when we tried to measure the contact angles of these materials to water, we ended up with such a superhydrophobic material that we really struggle to deposit even a drop of water onto the surface to measure the contact angle. So if, let's say, you measure contact angle, you usually have a pipette, and then you deposit this drop of water. But when we lifted the pipette tip up, that drop of water preferred to stay with the pipette tip, and it just lifted up with it as well. So that was a little bit challenging. And our material really kind of reminded us of how like water just like bounces off a duck's back. Eventually, we managed to kind of get a contact angle range of about 153 to 160. But the thing is, water is actually really easy to repel. So the creation of superhydrophobic surfaces is not so difficult to do. And the reason for this is that water has a really high surface tension. Now, if you were to move to lower surface tension liquids, such as with hexadecane, then you really struggle. And we saw this in our case when we measured the contact angle of hexadecane. It was 20 to 25, but we have a porous material. So to kind of add insult to injury, not only had a low contact angle, it even absorbed the hexadecane after a while. So we were really disappointed about this. And, you know, chemically speaking, we have already kind of brought out the big guns in terms of functionalizing this material because we've already fluorinated it. And so we can't really lower the surface energies any further, at least in our minds. So we thought, how do we actually repel hexadecane? There must be a way to do it. And we're pretty stubborn, so we thought, let's think about this a little bit. And came across this paper by Bob Cohen at MIT. And their group showed that through a multi-step process of lithography, they could create these kind of micro mushroom-like surfaces. And in these micro mushroom surfaces, they create this special re-entrant texture whereby they are able to repel not just water, but also oils. And this is very much a morphology-dependent repellent. And the reason for this is kind of like is explained here in this diagram. So let's say you have a structure with like these pillars with these etched microgrooves and a certain curvature. So in this case, let's say you have a liquid layer here. You've got your solid pillars and you've got some air in this gap. And let's say this solid line here is the liquid air interface. And here this point is that representing the liquid solid air contact line. So for this liquid to wet a surface with these kind of micropillars, that liquid needs to kind of penetrate further into this gap. But that requires a temporary increase in the contact angle of this liquid. And that is energetically disfavored. So what you're doing here is that by creating this special morphology, you're kind of stabilizing or creating an energetic barrier to create a local energy minimum to stabilize this state whereby even hydrocarbons can be repelled by this surface. So we thought, we've made MOF grass, MOF flowers, MOF seeds. Can we make MOF micro mushrooms? And so we thought, well, we've got these surfaces and they repel water. What if we just kind of take that and flip it upside down, put it in a beaker of liquid, and let it try to selectively grow a mushroom cap at the interface? And that's what we did. We took these amino MIL53, we functionalized it to fluorinate, then we stuck it in on a precursor solution. And so what happens at this kind of interface that's zoomed in here is that your air pockets really prevent this aqueous precursor from climbing up the walls. And so further nucleation and epitaxial growth is limited to the rod tips. And the idea would be that we then grow these kind of caps here. And indeed, we were able to do this with these little mushroom caps. And upon further fluorination of the caps, we end up being able to repel not just water, but also oil. And you see here that if you leave it for a little bit too long, you end up with these kind of MOF lollipops instead, because the liquid layer starts to like kind of crawl up these microneedles. But this was a fun little example for us of showing how one can exploit liquid air interfaces to control growth. We then looked at some other composite materials. So we used, in this case, gamma alumina again, but in the form of these particles instead of AAO membrane. And we found that like we could grow these MOFs onto the surface of these gamma alumina. And my students, they did some fluorination. And so they ended up with this kind of yellow MOF powder, which is very hydrophobic. So what they were doing is they like to have some fun in the lab, and these were some high school students. So they were playing around with some water droplets on this powder, and they dropped a drop of water droplet and they kind of rolled it around, and they found that actually what the powder ended up encapsulating a drop of water when you take this water and you roll it around in this powder. And then this drop of water is really cool. It doesn't wet that glass petri dish anymore. So here's a little video. Let's see if I can get this to work. So, and here you have a glass petri dish, which is hydrophilic. Here you have a drop of water, which wets the glass. Here you have another drop of water, but we roll this drop of water in a hydrophobic powder. And now you see that this drop of water seems to think it's on a super hydrophobic surface. And when we first kind of saw these kind of phenomena, we were like, whoa, you know, that is so cool. What is this? It's a little bit reminiscent of like a water droplet on a lotus leaf, right? And it turns out that these are what are called liquid marbles. So it's first described by Ocelus and Quera in 2001. And this is kind of a drawing to illustrate what's happening. So in the Cassie-Baxter model for a superhydrophobic surface, you have a rough surface with asperities, and then you've got air pockets, and then you have this liquid droplet sitting on top of the asperities and partially supported by these air pockets. In a liquid marble, instead of these asperities being attached to the substrate, your protrusions are attached to your liquid surface. And what happens is that if this liquid droplet rolls around, the particles therefore roll around with it, and it thinks that no matter where it rolls, it's on a very repellent surface. And so it's kind of like turning everything around on its head and looking at things from a different perspective. But this means that you no longer have to functionalize your surface, you just functionalize your liquid to make it think that it's on a super oleophobic or super hydrophobic surface. And if you kind of zoom in at the interface between the particles and the liquid, and one can do this via environmental SEM, if you use a high boiling liquid for your liquid marble, you see that there are lots of gaps in between these particles. In this case, this was the MOF particles I showed you earlier, and we had glycerol. And so we thought, oh, you know, maybe we could actually learn to encapsulate these liquid marbles by using some kind of interfacial polymerization. So what we did was that we exposed these liquid marbles to essentially just super glue or ethyl cyanoacrylate. And this molecule has the function of being very easily polymerized. You just need water, for example, and it starts to kind of initiate a polymerization and it just goes. So when we had this in a chamber with some superglue fumes, we found that like over time, you start to see like polymerization. So these are these little nodules, which is the polymer of superglue. And these are the MOF alumina composite particles. And if you leave it for long enough, you start to like really cover everything with this layer of polymer. So we've shown that like we can use in reactions also at interfaces to kind of functionalize these materials. Now then we thought, okay, so we've used air-liquid interfaces and we've like used them for growth as well as polymerization. What about liquid-liquid interfaces? And I always wanted to make Janus MOFs because then this would allow us to make little micromotors. And so this is one of the first examples, or really the second example of a MOF micromotor, but the first one using these kind of Janus MOFs. And in this case, what we did was that we exploited an oil-water interface, and we had ZIF8 particles. This is a zinc-based MOF. And if you disperse it, it will automatically want to go to typically an oil-water interface because surface energy is intermediate between that of the oil and water. And so we had PMMA dissolved in the oil phase, and then we let the oil phase kind of dry out. And what happened was that then you end up with a polymer layer with partially embedded ZIF8. And this is kind of a drawing to show what's happening. And then we took this and we did some further heteroepitaxial growth. So we took cobalt nitrate and 2-methylimidazole to grow ZIV67. ZIV67 is isostructural to ZIV8, but you use cobalt instead. And the reason we did this was because cobalt is redox active, and it could be used for a Fenton-like reaction for the breakdown of hydrogen peroxide. And so one could use this for micromotor movement. So we found that, yeah, indeed, we could grow kind of these Janus particles or two-phase particles where you have ZIV8 and then a little ZIV67 cap. And this is a false color SEM image where you have the ZIV8 and then you have the little ZIV67 cap here. And this is a little video showing what's happening. You have the ZIV67 and it starts to kind of break down H2O2 and you have bubble evolution. And so this was just a video taken with an iPhone by one of my high school students who was working on this. But it was a really fun like foray into this kind of chemistry, again, using interfaces. So we had a lot of fun and games here, but then we thought, okay, like maybe we should also think about some other serious problems of or limitations of MOFs at the moment. And one thing that really struck me was how important it is to be able to controllably orient MOF crystals. So there are more than 100,000 MOFs that have been prepared thus far or reported. And more than 97% of these MOFs have non-cubic lattices. So these lattices are anisotropic. And since structure is intrinsically tied to functionality, what this means is that when you have an anisotropic MOF, its function and its performance is very, very much tied to which crystallographic direction you're looking at. So take the example of MOF 74. So in this case, MOF 74 has these one-dimensional channels. And so you could imagine that these channels will have completely different mass transport than when you look at it perpendicular to the channels. And so it was found that the mobility of the protons is 1,200 times higher along these 1D channels. So besides mass transport within the channels, one can also consider how orientation enhances things like catalysis. So this is just one example of many, where in this case, the authors grew MOF on a nickel film. And they showed that when they had just vertically oriented crystallites versus non-oriented crystallites, that the catalytic performance was significantly enhanced in the vertical case versus the unoriented case. So we thought, okay, it's really important to orient MOFs. And actually, there has been quite some work. It's not been an unrecognized problem. There's been work to try to control MOF orientation. And a lot of work has been done to kind of control the growth of MOFs via kind of gel layers or layer by layer growth or per-sister conversion. But typically, this is very slow. It requires very precise control. But it does give you beautifully oriented MOF materials. You can also have directed growth on different substrates. So kind of like what I showed you was one example where you had the MIL-153 growing on an aluminum oxide membrane. So in this case, you need to also consider the compatibility of the substrate to your MOF that you're using. And you really need to consider the growth conditions. And also this can take quite some time. So the issue with both of this, or the shortcoming, is that most MOFs that are prepared today are not prepared in these kinds of manners. Most of them, by far, are synthesized as bulk, nano, or microcrystalline powders. And so if we want to be able to use these powders and integrate them into polymers for processing, for industrial use, and we want to be able to control their orientation, we have to move away from these kinds of control of MOF growth and look into the control of loose particles. So my group is focusing on using external fields to kind of manipulate these MOFs. and in doing so, kind of understand the mechanisms behind it and to see if this ends up with an improvement in their overall performance. So if you think about how to orient loose particles, I guess one of the first things that comes to mind is the use of magnetic fields. And so probably a lot of you as children have played with like a magnet as well as ferromagnetic powder or like iron filings, where you take this magnet and then you have this powder and you kind of move this magnet near the powder, and the powder kind of moves around along the field lines. So in this case, these authors took some ferromagnetic particles. This was quite a while ago, hence the quality of these images, but they controlled the orientation and alignment of their particles using a magnetic field, but they use ferromagnetic particles. Now, a clear and obvious limitation here is that you need ferromagnetic materials, right? Most MOFs are not ferromagnetic. So then the question arises, how do we use MOFs even if they're not ferromagnetic and use these magnetic field alignment to control them? And so one strategy to do this is to magnetize the MOFs. And we want to do this in a very simple way that is very, very widely applicable to all sorts of net-organic frameworks, not just one or two examples. But in this case, we took amino-MIL53 because, well, to be honest, we had that. And also it's a needle-shaped MOF, so it allows us to very easily see that orientation almost immediately. And we took NU1000, which is also, in this case, a rod-shaped MOF. And both of them are very anisotropic with one-dimensional channels. So they both have isoelectric points of 10.5 and 4.3 respectively. So below these isoelectric points, if they are in a pH of, let's say, like 3, these MOFs happen to be positively charged. So, and then we took some iron oxide nanoparticles, and these nanoparticles have an isoelectric point which is quite low, of 2.8. Above this isoelectric point, these particles are negatively charged. So you see where I'm going with this. So if you have positively charged MOF crystals, negatively charged iron oxide, these are already preformed. You just kind of mix them together and they then stick to one another. So these iron oxide nanoparticles that we synthesize, we mix them and then they just kind of stick onto the external surfaces of our already preformed MOF crystals. And this is a very universal approach. You can pretty much, just by playing with which pH condition you use and the functionalities on your iron oxide or other types of magnetic nanoparticles, really just create a magnetic envelope around your MOF crystals. We then dispersed this in different types of polymer resins, and then we molded them in the presence of a magnetic field. And you can see here a little video of how rapidly they can align. So of course, how rapidly they align depends on the viscosity of the liquid, but we were still able to very easily cause this orientation even in really viscous resins and photopolymers. So, sorry. We found that actually if we were to orient these MOFs inside a resin, so in this case we used NU1000, so you see that here they're kind of aligned in the diagonal direction and here they're all randomly oriented. These particles don't have as high an aspect ratio as the MIL53, so the alignment is not quite as easy to see. But we saw that actually if you shine upon these particles linearly polarized light kind of along the longer axis of these MOFs, that actually they have an anisotropic fluorescence response. So NU1000 has these pyrene type linkers, and these are fluorescent moieties. So if you shine the light like in this direction, we get the maximum fluorescence response versus if we shine the light perpendicular to the MOF crystals. And of course, in the unaligned MOF, you don't get really a directional response as such. One can integrate this quite easily also into 3D printing simply by just incorporating neodymium magnets and then just printing it. You can get, of course, much more complex architectures than these hexagonal materials, but these are just a couple of examples, and you can plot the orientational distribution, but you can see that there is a clear preferred orientation. However, we thought, okay, you know, magnetic field alignment, it's very, very simple to apply, but unless you're using electromagnets, it's not quite as versatile and not as easily tunable as electric fields. Also, if you use electric field induced alignment, typically you get a little bit less crosstalk and it's easier to integrate into electronic devices. And you can do this across very small areas, very precise areas. So we thought, okay, you know what? We should really move to electric fields and use them to align MOF materials. So if you consider a particle or a rod or any material really, stick it inside an electric field. If you have appropriate frequencies and appropriate polarizability of your particle, you will induce a dipole in your material. This induced dipole forces these particles to align, and so that you get a torque, and then these particles then align along the electric field. This is very frequency dependent. So let's say if you use low frequencies of your electric field, then you kind of induce a dipole via ionic movement. And if you use higher frequencies, you can induce dipoles via these kind of dipolar polarization and so on. So typically we stay in this range here because that's the limitation of the instruments we have. But what we did was we first took NU1000, and this MOF is a really nice workhorse because it's very easily synthesized in a monodispersed fashion. Also, it happens to be fluorescent, so one can easily observe it using confocal microscopy. And if you disperse these particles in a nonpolar solvent, such as bromobenzene, because these particles still have a zeta potential, so when you disperse them in a nonpolar solvent, you get very little solvent and ion shielding of these particles. So you get electrostatic interactions that are felt between these particles, and they repel each other. So what happens then is that because of this repulsion, these particles end up being dispersed in a very uniform manner, and you have basically positional order. Now, if you then have this suspension and you put it inside a capillary and you expose them to an electric field, you end up very rapidly kind of creating not just particles with positional order, but also directional order. And you have these kind of pictures that you see. And this can also be observed under polarized optical microscopy. So you have two cross polarizers. And because NU1000 happens to be birefringent, so if you look at it through cross polarizers, you will see your MOF particle as kind of a bright spot. And this here at the bottom is just a drawing. This is the real image that we see in the polarized microscope. And so when these MOFs are randomly oriented, you see a bright image because of the relatively large light transmission cross-section. However, if your particles are vertically oriented, kind of like coming out of your monitor, then you end up seeing a darker image. So we can actually follow this by attaching a photodetector to the optical microscope and then hooking that up to an oscilloscope and then kind of just plotting the graph. And we see that when the E field is on, you get a dark image, so low light transmission. But then if you turn it off, you have relaxation. And then it goes up to a brighter image. And then once you turn the E field on, very fast, you get a response, you get a drop in the light transmission. And so that response time is about 0.1 second, although it could in reality be lower because that was kind of the limitation of what we could observe with our instruments. And you see that here, this is a little video of what you actually observe under the optical microscope. So now I've shown you that we can use electric fields and magnetic fields to kind of orient MOF crystals. And so we thought, well, can we also pack them into oriented assemblies? And this actually was kind of inspired by biology once again. So take this example of the mantis shrimp. This is one of my favorite creatures. So cool, right? It's very beautiful, but also it's a really badass animal. So you remember I mentioned like you've got seashells, and this is made of calcium carbonate, but they're incredibly tough. They can withstand impact against rocks to help their animals survive. Well, this guy here actually takes its ductile club and it smashes these seashells and then eats the mollusk inside. So it does that for like all sorts of prey. And so this ductile club has to be able to last a lot of impact. And it's actually one of the toughest materials out there with very high impact resistance. And the reason it can do this is because it has this very complex architecture, which is kind of like a cholesteric or chiral liquid crystal. So it like kind of grows like this. And it's thought that these structures actually create this very beautiful architecture, starting from chitin and different proteins, well, primarily chitin that then is biomineralized. And so the chitin self-assembles into liquid crystalline structures that is then mineralized and allows these architectures, which are very, very good at dissipating impact energy. You also have these scarab beetles, which have similar types of architecture, very, very complex, and they can reflect circularly polarized light. But besides molecules or polymers that can form liquid crystalline phases, particles can also do this. So particles can form these nematic phases, whereby they have these kind of directional preference. They can form smectic phases, where you not just have direction, but also the formation of layers. And you can have, if you have chiral interactions, they can form these cholesteric crystals, like in the case of these mantis shrimp, or they can form discotic liquid crystals as well. So we thought, well, you know, there are examples of particles forming these. Why not MOF materials? And MOFs are especially exciting because you can really tune these particles for liquid crystal assembly. So in liquid crystal assembly, the prevailing theories are that, you know, you have an isotropic system, and if you have particles of sufficiently high aspect ratio, LD, which is represented by the length versus the diameter, it has to have an aspect ratio of at least 4.7 for it to favor the packing into nematic phases with this directional preference. If you have a very monodisperse sample, low polydispersity, then you can create also layered order to create these kind of smectic type phases. In this case, you don't need as high an aspect ratio, but it's still pretty high. Now, some of you might be looking at this and thinking, hang on, you know, most MOFs don't have aspect ratios that are quite this high. So what do we do then? And we thought, well, maybe we could cheat a little bit and exploit packing interactions together with electric fields to kind of be able to apply these kind of packing to crystals that have low aspect ratios, lower than this minimum of 4.1. So what we did was that we synthesized a bunch of different types of MOFs with different types of aspect ratios, so ranging from about 10, very, very polydispersed, to about 1.2, and this was a little bit more monodispersed. And starting with the MOFs with the highest aspect ratio, amino MIL53 in this case, we then dispersed them in a solvent and then filled these glass capillaries with our suspension. And then we had these glass capillaries sealed and vertically standing. So we allow these particles to slowly sediment from the top of the capillary all the way to the bottom. So you get denser packing at the bottom, and you can kind of observe what they look like over time. And we found that our top layer here, in the absence of an E field and just gravity, you see that you do have some kind of directional preference. But then as you go further down and you increase packing density, you end up indeed having a very oriented assembly. However, if you move to a different setup where you actually do apply the electric field, then you see that regardless of the packing density, throughout the whole capillary, that MOFs are very nicely oriented, and you get closely packed crystals here with this orientation. We then see that, like, also besides that with MIL68 with a lower aspect ratio, we found that also we do get some kind of preferential orientation when you have high packing density in gravity without an electric field, but it's not perfect. And here you really don't see much directional preference at all. And the reason for this in this case is that even though its aspect ratio is theoretically much higher than the requisite 4.7, you have also a very fast sedimentation. And what happens then is that when you have rapid sedimentation, the particles get arrested in these jammed states where they are not in their thermodynamically most favored situation with like this perfect packing order. Now, if you apply then instead an electric field and you pack them, you see that regardless of where you are in the capillary, once again, you get very beautiful orientation. And then we moved on to particles of much lower aspect ratio, 3.4 in this case. So this was exciting because this was lower than the minimum that we require in the absence of an E field. And we found that indeed these particles actually align very, very beautifully. And in the absence of an E field, you see that like they kind of like, yeah, do go pretty much a lot of every which way. However, these particles are very monodisperse and they have a higher monodispersity than is required to form the smectic phases I showed you earlier. So here you do see a little bit of a tendency towards like the formation of layers if you look at these kind of adjacent layers here. But if you look at it closely, the neighboring particles are not like perfectly or standing next to each other like soldiers, but rather they're kind of shifted or staggered relative to each other. And the reason for this is that you have to consider how we achieve this packing. So we used an E field and we induced a dipole in each particle. So if let's say I have positive on the right side and then negative on the other side, and then I have a neighbor that has also the same dipole, they don't want to be next to each other, but rather they want to be staggered and offset. Otherwise, they will end up having electrostatic repulsions. And that explains why we don't end up with a smectic phase. Now, if you move on to even lower aspect ratio 1.2, which is easily achievable for a lot of different types of MOF crystals, we saw that still we get a very strong preferred orientation, as you can see here, and very easy assemblies. We can get this in about like 10 to 20 minutes without any issues. So with this, I've kind of showed you that we can actually, through the whole range shown here of aspect ratios, we can really control MOF orientation and packing. And we can actually do this across almost centimeter scale assemblies. So now let's say if we were to take, I've shown you a lot of different ways of controlling MOFs. What about an example of a use? And one thing in nature is that you've got lots of examples of responsive materials that are able to kind of shape themselves or act as actuators. And you can think about the pine cone, for example. So in a dry pine cone, you have like these areoles and they are kind of standing horizontally and you have it open. But when this pine cone is immersed in water, this layer, this bottom layer of the areole actually starts to swell and stretch. And this top layer stays the same. So it ends up expanding in this way and it curves and then it ends up closing. So people have taken these kind of like ideas on board and used this with MOFs for responsive actuators. So a classic example is MIL88A. This MOF is chosen because it's got a very large volumetric response in the presence of water. It actually almost doubles its volume when it takes up water. And the Masport group has actually shown a couple of examples where they disperse MIL88A in a polymer matrix. And they see that like if they have a gradient in the density of the MOFs, so at the bottom with more MOFs, then you have more swelling at the bottom. And then you can end up with this kind of actuation and you have absorption, desorption, and you end up with curling and straightening. However, if you look closely at how MIL88A expands, so if you go from 20% humidity to 90% relative humidity, it expands 33% in this direction. But along the C-axis, it actually contracts about 18%. So what this means is that if you have these particles and you have them randomly oriented inside a polymer composite, these swelling and shrinkage start to cancel each other out. But if you have them beautifully packed and aligned, theoretically, you would be able to really harness these crystal-based anisotropy and translate that to the macroscopic length scale. And so we synthesize these MOFs and we disperse them in solvent in the presence of an E field. They align very nicely. And we fix them inside different types of polymer matrices, but primarily we worked with PEGDA, polyethylene glycol diacrylate, a photopolymer. So in this case, we can either align them using an electric field, and we do that very fast and we fix it. So you don't really get quite a homogeneous dispersion, or you can let them kind of sediment a little bit so that you have a kind of gradient in the density of the MOFs as you go towards the bottom. And here you have your unaligned films where you see the MOFs are randomly oriented. Now, if you look at the aligned versus the unaligned film, you actually see that there's a huge difference in the performance. And in this case, we use a lot less MOFs than what is typically used in previous examples of MOF actuators. Here we used about, I think, 18 to 20%, whereas in previous examples, typically they need 50% of the MOF. And you see that alignment makes a big difference in the response. Here are a couple videos. So here you have the underline and here you have the line. And not only do you see that there's a difference in the extent of the curling behavior, but also a difference in how fast it actually starts to curl. And we saw that we can actually cycle this, like it can absorb and straighten over 20 cycles. And then I think the postdoc got a little bit fed up with continuing this, but probably could go further. And you have this film and it can actually move 28 times its weight for a distance of almost a centimeter against gravity. And so with this, I hope I've kind of convinced you of the importance of MOF alignment as well and how particle assembly is actually a promising approach. And if some of the examples that I've mentioned to you today has kind of intrigued you, I encourage you to read a couple recent publications. I had the honor of being involved in a paper from the Falcaro group, where this is a perspective on the fabrication of oriented MOF superstructures. And here we have a review from my group where we looked at a multi-length scale hierarchy in MOFs as well. And with this, I thank you very much for your attention and your patience with me. I've gone a little bit over time and apologize. I need to thank also my collaborators, the students who actually did the work, my current group, as well as the funders for all their support. So thank you once again, and I welcome any questions you may have.
Thank you very much, Jami, for this excellent presentation. We do have some questions, but before that, maybe I can try to ask some questions first.
Yeah.
My first question is I want to know you have demonstrated some MOF, I'm especially interested in the responsiveness of the MOFs on the external electrical field. So I'm wondering, do you have any requirement about the particle morphology in order to observe this kind of alignment?
Yeah, that is a question I like. All the sharp professors who are eagle-eyed are like, that is the killer question. And it's true, you need a certain aspect ratio because, as you have obviously noticed, you need to have a torque to force them to orient, right? So imagine if you have a very low aspect ratio, let's say you have like almost a spherical type MOF, then you don't have a preferred orientation that is strong enough to overcome thermodynamic kind of like random thermal influences to cause it to kind of like vibrate. However, it doesn't mean that if you have a MOF that has a low aspect ratio, you cannot orient it. There are a lot of tricks to do this, and you can increase the polarizability of your particles by, for example, making them a little bit more conductive, or by incorporating salts into your MOF materials, because then you enhance the ion migration. And so the ion induced polarization. So if you do this, let's say I have a MOF like MIL68, and I have a low aspect ratio of 1.2 or even lower, let's say 1.1, or even if I have an aspect ratio of almost 1, we can see that you can get a preferred orientation if you choose the right frequency, and if you have conditions to really support that.
Okay, that's very interesting. Have you tried the MOFs with nanosheet morphology?
No, we haven't. We would be really interested in that, but we don't synthesize MOFs with nanosheet morphologies at the moment, so we haven't tried it. In that case, it might be a little bit more complex. If you want like a 3D kind of orientation, so you can probably align, let's say you've got a sheet and you've got like an E-field going this way, you can probably align it in this way, but then they might be like rotated like in this direction and you might not be able to control that. So there are ways to kind of play with that, but it's a lot more complex.
Yeah, just a suggestion because there is a very strong interest of aligning the MOF with a 2D morphology in the mixed matrix membrane. So I think your technology will be very useful for that purpose.
Yeah.
Yeah, last question from me before I start to go to the Q&A. Have you tried 2D or even 3D electrical field?
We have not tried 3D electric fields. We have started to look into 2D electric fields.
Yeah.
But so 2D electric fields are a little bit more complex. You get crosstalk and all that stuff. And we're also starting to look into like combinations of magnetic and electric fields. But then it gets way more difficult. And then you also have to have very good and very patient students. And so you know, there are a lot of hopes and dreams, and then there is some difficulties.
Okay, good luck. So let's
Thank
move
you.
on to the Q&A from the audience. So maybe I will just start from the Q&A text box. I noted there are some questions in the chat box, but the chat box is just too long. In the interest of time, I will just pick up some questions from the Q&A. If you're really keen to have your question being answered, please type your question in the Q&A box. So we'll start from the first. So Jamie, feel free to answer. If you think some of the questions are not quite related with the topic, you can ask me to answer.
Okay.
Yeah, I'll try my best. The first question is, Lincoln wants to know more about the recommendation regarding synthesis of MOF materials or MOF composite materials for electrocatalysis application. I'm not sure whether you have any experience on electrocatalysis, but
I don't have experience on electrocatalysis, but one thing that we do observe and we think is really important is that if you were to use perform electrocatalysis, one thing that is a key problem is the formation of bubbles and how these bubbles then like really decrease the effective surface area of your electrodes. And you really want to like have morphologies that allow bubble evolution. So that is one thing that we also have considered for controlling MOF orientation.
Okay, thank you. The next question from Kenichi. Which properties of the MOF composite led to the formation of liquid marble? Is aluminum oxide core or particle size important?
It doesn't matter what type of particle you use in terms of material, but the contact angle of this particle or the surface energies of the particle is extremely important. So let's say the angle towards water, if you want to make a liquid marble with water inside, it must be able to repel water. So that is how you play around with particles. You can use silica, for example. It doesn't have to be a MOF.
I see. Okay. So Tian is interested to know the application of the magnetic properties of MOFs.
Well, specifically for our case, we were interested in kind of just using it as an easy entry to alignment. But this would really allow you to kind of integrate them into different kinds of composites and integrate this into processing and then control their orientation for, let's say, formation of membranes and so on.
Yeah, maybe I can add a little bit more. The magnetic property of MOFs definitely can be used to align the MOF particles for membranes for device. Also, from our previous speaker of the webinar, Professor Matt Hill, he introduced the magnetic MOFs for regeneration of the adsorbent. So just by applying a switch of the magnetic field, he can generate heat, and that heat can be used to heat up the MOFs and release the adsorbed gas like CO2. So that is another application, nice demonstration of the potential application. Okay, so Abe asked the question whether you have any experience with the MOFs with a mixed linker. And the new morphology produced is like a combination of both of the original MOF with one linker. And what is the easiest way to produce hierarchy pulse on MOF?
Okay, so the first question, the synthesis with mixed linker, it is quite commonly done with certain MOFs. Like a classic example is I think UIO67, where some people take a bipyridine dicarboxylate as well as the biphenyl dicarboxylate, and they mix them, and then they grow UIO67. And because the sizes of the linkers are so similar, they can kind of like be incorporated very easily into the lattice. And then you have sites which are able to bind other metals arising from the bipyridine. And the new morphology that was produced in this specific case is pretty much the same as the old morphology. I personally don't have experience with other types of mixed linkers, but I think there's quite a lot of literature out there on this. And the easiest method to produce hierarchical pores, I think some of the earlier examples people use is surfactant templating. So like they have micelles and self-assemble, and then they kind of grow MOFs around these micelles. So you end up with like mesopores due to these micelles that they then wash out, as well as the nanopores arising from your MOF's architecture. But now there's like some people who are using, for example, polystyrene beads, and then they grow MOFs around them, and then they dissolve the polystyrene beads. And so they get these kind of inverse opal architectures.
Yes, just to add up, there are some other methods. For example, you can deliberately introduce defects into the MOF framework to introduce hierarchy pores. Okay, another question is how to make the MOF hydrophobic, particularly MIO 1 to 5 amino. Any particular criteria to follow?
I think amino MIR125 is probably a relatively easy MOF to hydrophobize because it's quite stable. And so you could treat it with some kind of acid anhydride, which has, let's say, a hydrocarbon or fluorocarbon chain, or even an acid chloride. There are a few examples, for example, from Seth Cohen's group, as well as my group, where we have made these different MOFs hydrophobic. And I think the similar strategy would be applied here. You just mix them with like your reagents carefully, slowly. And if they are sensitive, you try to do it a little bit cold.
Okay. In the interest of time, I will just pick those questions that are highly related with today's talk. So Jieyun has a question. The dipole orientation is very important for nonlinear optics. The optical switch manipulated by voltage may be used in optical waveguide devices. Do you test the switching speed? If the switching speed can be megahertz or even gigahertz, this will open a new avenue for MOF in photonic devices. Thank you very much for the question, also the suggestion.
That's actually a really cool question. Thank you for that. With regards to the switching speed, we didn't have the instrumentation to do that. But if, let's say, you might be interested in that, I'd definitely be interested to talk to you about it. But the limitation of our instrument would not allow us to test this.
Okay. Yeah, I hope that your lab can develop further devices methodologies.
Well, I
Yeah,
mean, the optical switching would be very cool.
Yeah, sure. And Jean is from my group. She asked a question. For the growth of microscale single crystals, the morphology may depend on the growth rates of the different crystal faces, and the preferred orientation is generated. Are there any good methods to control or change the preferred growth orientation of single crystals? Thanks.
Yeah, so the classic method is just coordination modulation. So like in the one example I showed from the Kitagawa group, they actually showed that if they use a carboxylate linker and they treat this copper NDC dapcode base MOF, which happens to be a MOF whereby you have this NDC, this dicarboxylate, which grows 2D sheets, and then these 2D sheets have pillars of dapcode in between. So you can imagine that like if you want to modulate the growth of these sheets, that you have a carboxylate-based modulator that competes. Whereas if you want to modulate the stacking of these sheets, then you have a kind of pyridine-based modulator that kind of competes with your DAB co-linker. So you can selectively modulate surfaces. That's one way. Maybe Zhao has some suggestions to add. I don't know.
Yeah, I think we have a lot of failure experience on that.
Okay.
It's not easy, but I got a lot of inspiration from your talk. Now I realize that it is actually the interface. I really like your figure where you show the air, the solid, and the liquid, the interface, and you show the diagram with a micro groove and the curvature, and how the formation of the liquid layer can help to stabilize and prevent its further penetration into the material.
Yeah.
Yeah, I think that, I mean, for that level of understanding, it's very important, but I personally feel it has been mainly not have been paid attention in this community, the interface and the colloidal systems.
Mm-hmm.
Yeah, so I think that your study nicely fit this gap, and we are all very excited about your presentation today.
Thank you. That's super kind of you.
Yeah, thank you. So in the interest of time, we'll just end today's webinar. So please join me to thank Jami again. Thank you very much. Yeah. So again, we will have our MOF 2024 series webinar every month. And we've shared the registration link for next month. And please register and join us online next month. Thank you all, and we will end the webinar today.
Thank you very much, Dan, for this opportunity. And thank you, everybody, for your time.
Thank you. Bye-bye.
Bye-bye.